Hi, everybody. This is Annie Bauer. I'm an assistant professor at University of Wisconsin-Madison in the Department of Geoscience. And my background is that I'm an isotope geochemist and geochronologist, largely focused on crustal evolution and also the rise of atmospheric oxygen. So today, the conveners have asked me to talk about the oldest continental crust that we have and chemical crustal evolution on Earth. And I'd like to thank them for inviting me to share this with you. This image on my cover slide is of the Acasta Gneiss complex in the Northwest Territories in Canada, which is some of the oldest continental crust we have. And I like this image because it's taken from a helicopter, and from the context of this image, there are multiple outcrops where there are rocks that are 4 billion years in age. One right underneath the helicopter, one out here on this feature, and one just off of this image over to the left. But before I dive into that, I want to take a step back and come back to a paper from 1983 that's very well known in our field by Campbell and Taylor. And the title of this paper is No Water, No Granites, No Oceans, No Continents. And they really get to the point in the abstract. They say water is essential for the formation of granite, and granite in turn is essential for the formation of continents. Earth, the only inner planet with abundant water, is the only planet with granite and continents. The moon and other inner planets have little or no water and no granites or continents. And so this underlies how we think about the evolution of our planet and continent formation in particular. And so there are some really nice points that are raised in this paper, and one of them is thinking about the crust as a buoyant body and how do we actually get buoyancy of the continental crust. And ultimately that's the formation of felsic magmas. And so one thing that we're going to explore next is talking about felsic magmas on the early Earth and thinking about how they formed and what we know about that. And a critical part of that ties back to this Campbell and Allen paper and thinking about having water in the source to these magmas. And so an important constraint ends up being, how do you get water into the source? How do you get water back to depth in the earth such that it can participate in melting? Once you have a sufficient amount of buoyant crust, and therefore it'll be gravitationally stable, it can resist destruction through subduction. And that's how we actually get continents and maintain them on the earth. In this plot, I'm showing a change in the composition of granitoids over time. And on the y-axis, we're looking at the concentration of ytterbium, and the x-axis, the lanthanum to ytterbium ratio. So these are both rare earth elements that are from the lanthanide series in the periodic table. This inset actually shows that succession from lanthanum out to ytterbium and lutetium. These are all 3+ cations that behave very similar geochemically. And so it's useful to look at them because they have slightly different ionic radii, with smaller ones out here at lutetium and larger ones back here at lanthanum. You'll notice for these profiles here where they're showing the concentration of these different elements normalized to the bulk earth, that the slope for or profile for Archean granitoids, which are called TTGs, those are tonalites, trondjhemites, and granodiorites, is pretty different than granitoids that are younger than 2.5 billion years old. And that's also shown here in this plot. This lanthanum to ytterbium ratio is basically showing the slope in these two subsets here. And then this is showing the ytterbium concentration. So the younger granitoids have higher amounts of ytterbium, but really low lanthanum to ytterbium ratios consistent with this slope here. And Archean TTGs, on the other hand, have a large range in lanthanum to ytterbium ratios, which is consistent with some of these steeper slopes in this diagram. The thing that's really controlling this is the mineral garnet. And so I'm going to put here a plot showing the concentration of these different rare earth elements or lanthanide series elements relative to the bulk earth and how they would partition into the mineral garnet when it forms. And garnet basically gobbles up heavy rare earth elements. It takes a really high amount of them, many more orders of magnitude more than light rare earth elements. And it's one of the only minerals to do this in an appreciable way, such that we know it's the major control on the difference between these TTGs and these post-Archean granitoids. And so what's going on here is this strong fractionation of lanthanum to ytterbium in these Archean granitoids is because there is garnet in the source, preferentially taking up ytterbium and driving up the slope, the lanthanum to ytterbium ratio of the granitoids. So ultimately what this indicates is that there's melting at a depth of about greater than 40 kilometers or so, based on our understanding of where garnet is stable. And when we think about the stabilization of continental crust and its buoyancy, we need to think about the formation of cratons ultimately. And it's a long-term process that proceeds in multiple stages. And so I'm showing this with this diagram here on the right from Laurent et al., where they are showing a timeline from about 3.2 billion to 2.4 billion years ago for a variety of cratons across the world. And what they're trying to highlight here is that TTGs, the thing that I mentioned before, these sodium-rich granitoids fall into these yellow phases here. And that TTG formation lasts quite a long time in these Archean granite or cratons. And then ultimately, there's a transition to the emplacement of late Archean granite blooms, and that's these last magmatic phases here, kind of tying up craton formation in these areas. Beyond that, another thing we need to think about is how did Archean felsic magmas form? And a lot of experimental petrologists have worked on this and have determined that it's from melting of hydrated basalt. And so the way that it works is basically you partially melt the mantle and you form a tholite, so you form a mafic rock, and then you need to partially melt that and leave some residue behind, but then extract some melt, and that ends up producing a tonalitic melt. And then that can fractionally crystallize and leave some things behind as well, but ultimately these end up forming TTGs, which I've referred to before, which are tonalites, trondjhemites, and granodiorites, which are sodium-rich granitoids. These images from Moyen and Martin are showing two different ways that you can actually melt hydrated basalt to form tonalites, trondhjemites, and granodiorites. And unfortunately, it's not diagnostic of a particular tectonic setting. There are actually two really different types of settings that you can do this in. This first one is shown very simplistically here on the left. We have a mantled plume coming in and actually development of an oceanic island type structure here. And as it over thickens, you can actually remelt it at depth. And if there's hydrated material at depth, that can be hydrated basalt that can melt to form TTGs. Another model requires subduction. So in this case here on this left-hand part of this panel, subduction of oceanic continental crust that's hydrated below the continental crust. And in the Archean, if it's hot enough, it can directly melt that oceanic crust, and that can form TTG magmas. The right-hand panel here is actually showing the same thing, but just later in the Archean with a slightly cooler thermal regime. And in this case, it involves direct remelting of the oceanic crust, which is different than we see in subduction zones today. But another question that comes up then is how do we actually get water to depth to melt? And so I mentioned that hydrated oceanic crust is being subducted and melted at depth in the Archean as a potential plate tectonic-like scenario for the formation of TTGs and granitoids. But how does that actually work? This is shown really nicely in this cartoon here, where there's a mid-ocean ridge on the left-hand side. And when you're generating new oceanic crust, there's extensive hydrothermal circulation cells developed that are ultimately altering minerals at low temperature and ultimately hydrating them. And so that crust gets transported and chemically binds the water and hangs onto it, and might even get faulted a bit more extensively and serpentinized as it's being subducted, but ultimately carries all those hydrous minerals down to depth. A non-plate tectonic model for getting water to depth and then melting basaltic precursors that are hydrated to form granitoids is shown here in this figure from a paper by Tony Kemp et al., looking at the Jack Hill zircons, which we're going to step to next. So in this left-hand panel, what they have depicted in this cartoon here is a hydrothermally altered and hydrated basaltic crust that's at the surface. And they're using oxygen isotope compositions, which we'll talk about later as kind of the basis for this model. But basically it's hydrated. And then emplacement of magmas on top of this in a volcanic pile, which is shown here in cartoon B, where you've developed this big volcanic pile on top of it, causes remelting of some of this basaltic precursor at depth here. And so if we zoom in on that, that's where the Jack Hill zircons or granitoid-like magmas potentially could form that have been hydrated. Let's talk about the Jack Hill zircons. Many of you will be familiar with them. They're from Western Australia, and they're the oldest vestiges we have of early continental crust on the Earth. The oldest one is 4.37 billion years old, and they track all the way to about 3 billion years ago. Most of the attention has been focused on the ones that are Hadean in age, so anything that's over 4 billion years old, because there are not many rocks from that time in Earth history. On the left-hand side here, we're looking at the outcrops of these metasedimentary rocks that you would sample if you went to work on these in Western Australia. And this middle image here is showing you the two different types of rock that people find these detrital zircons in, which are metaconglomerates like this down here and metasandstones like this up here. So the zircons themselves are no longer in the rocks in which they form, but they've been weathered out into a sedimentary rock, and then we can collect them and analyze a variety of geochemical parameters in them to make inferences about the rocks in which they formed. These images on the right-hand side here are cathodoluminescence images showing kind of a zoomed in feature of pieces of zircon. from the Jack Hills complex. And these are pretty small overall. The scale Bauer for this one is 50 microns across, and for reference, a human hair is about 100 microns width. So this is a really small amount of material that we're working with here. Zircon is a zirconium silicate mineral. It's a robust little capsule of geochemical information. When it forms, you can think of it like an onion. It'll be growing in a magma and incrementally adding layers to it. Those layers can trap inclusions of other minerals from the magma in them, giving us information about the source rock, which we'll talk about in a minute. The zircon can also take uranium up into its structure, so it is datable using the uranium-lead chronometer. It's also very resistant to metamorphism and alteration, so it's pretty useful overall in evaluating a variety of geochemical parameters. One example for that is looking at the oxygen isotope composition of zircons. And so looking at the relative amounts of oxygen 18 to oxygen 16, which has been used for these zircons to infer the presence of oceans on the Hadean Earth, essentially. And so the way that this works is that this oxygen 18 parameter has a range that we know that's approximately what we see in Earth's mantle. So that's shown with these dashed lines here. And if we look at the Jack Hill zircons over time from about 4.37 billion years ago to 3 billion years ago, you can see that the oxygen isotope compositions scatter away from that mantle composition quite a bit. The ones that are higher than the mantle composition here are relatively enriched in oxygen 18, which indicates that the magmas from which they formed, if these are robust signatures that are being recorded in these zircons, involves that supracrustal material had to undergo low temperature interaction with water, basically at Earth's surface. And then that material had to make it deep enough in Earth's surface to be incorporated into a magma. And so what the basis for this entire argument for the existence of an ocean on the early Earth is some of these positive signatures here in the Hadean Jack Hill zircons. As I mentioned earlier, another thing we can look at are inclusion assemblages. So minerals that get caught up in the zircon as it's crystallizing. And these have been used to argue for a composition that is felsic and relatively paraluminous, so having a lot of sedimentary and high aluminum content in the source to these Jack Hill zircons in the Hadean. And the basis for this is the presence of both muscovite and quartz, which is consistent with formation in granitic melts. And so a lot of the Jack Hill zircons have quartz and muscovite inclusions in them. But the nature of the inclusions has also been questioned by quite a few people. There's a nice paper by Elizabeth Bell right here that I'm citing, where she's actually gone in and evaluated where the inclusion assemblages are relative to cracks and other annealed cracks and other features that you might find in the zircons to try to distinguish between what could potentially have been altered and what might actually still be primary. Regardless, there's a paper by Rasmussen et al. Evaluating some accessory phases that are inclusions in these zircons and verifying that they're much younger in age and that there are also metamorphic inclusions. And so the debate for this is still ongoing. The final thing that I'm going to talk about for the Jack Hill zircons is that their concentrations of titanium in them have been used to infer the crystallization temperature of the zircons. So basically what these researchers do is there's a model using the partitioning of trace element titanium into the zircon lattice, and that's used as a proxy for the temperature of formation. This plot on the right-hand side here is showing the relative amount of zircons smoothed with this black line here, and their titanium and zircon inferred temperature, which is actually fairly low. It's between 600 and 800 degrees for the bulk of the Jack Hill zircons, and that has been interpreted to be consistent with formation in granitic magmas, and so relatively low temperature formation and not formation in relatively mafic magmas. This again has been questioned by others who cite that the titanium isotope or the titanium concentration calculations have assumptions inherent in them, and so it's unclear if these are truly diagnostic for crystallization temperature or what kind of inferences we can reliably make about the source rocks on this basis. So the picture that's been painted based off of the Jack Hill zircons is a complicated one because there are debates about all these different pieces of evidence that I've just given you examples of. And so this figure here, for example, is showing a list of observations made on the basis largely of the Jack Hill zircons ultimately feeding into speculations about the type of crust in which they formed and what we know about the presence of an ocean and things like that early in Earth history. But as I hope I've just communicated, it's quite complicated. And so there's a bit of caution here that's involved. And if I recolor some of these with traffic light colors to indicate how much discussion of the viability of these observations has kind of been ongoing, so we can think about what's underlying ultimately these speculations. You can see that it becomes a much more complex picture. So one thing that we can do instead of going in circles on this sometimes is we can find other vestiges of old crust that we can look at and look for more intact chemical packages. Unfortunately, there's not a lot of it. I'm showing in this map here with pink where all the Archean continental crust is located on Earth. You can see it's globally distributed and overall quite sparse. And what we're going to do first is we're going to zoom in on some of the oldest packages of crust up in this area here. So we're going to start with the Isua terrain in Akilia and Greenland. These are some of the oldest rocks that were found quite a long time ago, several decades ago. And this image here is showing on a map where these rocks are located in Greenland, where the ice sheet has actually receded. We have outcrop of them. And most of the rocks in this area are about 3.7 to 3.8 billion years old. They comprise quite a large range of rock types. They're mostly relatively mafic rocks, and I'm trying to show that here with these pillow basalts. This nice image of pillow basalts here where you can see the rind on the pillow basalt as it was erupted into water. They're also supracrustal rocks, so here's a nice conglomerate from that area as well. And so there's a range of rock compositions there, giving us kind of a better idea about greenstone belt formation at this time. Akilia Island has also been mentioned in the early Earth community as having a record, potentially a geochemical record of vestiges of old life in those rocks. I'm not commenting on that so much today because I'm assuming that will be coming up in another talk in this series. But one thing that has come up and has been extensively debated about those rocks is whether or not they were actually sedimentary originally before they were metamorphosed, and about the veracity of those signatures. Another place with old continental crust is the Acasta Gneiss complex, which is located in the Northwest Territories in Canada, which you can see in this inset map down here. I'm showing here a map of the slave craton, which is where the Acasta Gneiss complex crops out. It's here on the western margin. A tectonic window kind of exposed in a Proterozoic origin that has overridden the edge of this craton. The rocks here are relatively felsic compared to the ones we were just looking at in Isua, and they also do cover a range in composition. So there are amphibolytic gneisses, there are relatively felsic or TTG-like gneisses too that have been highly strained. There are banded gneisses that it's impossible to evaluate if it's a juxtaposition of multiple rocks or if it was one precursor rock that has been highly deformed and strained. There are also foliated granitoids that have relict igneous features left in them too. And so there's kind of a wide range of rock types, and there's a rich magmatic history from about 4 billion years ago to about 3 billion years ago in this region. But on the whole, it's a complex mixture of metamorphosed rocks. And so one of the things I want to convey here, and in talking about Isua and Akilia, and the next place I'll talk about, which is the Nuvvuagittuq Supracrustal belt, is that a lot of these rocks have been extensively deformed and metamorphosed, which makes working out their history quite complicated. So Rick Carlson mentioned the Nuvvuagittuq Supracrustal belt in Quebec in his talk last week, and these rocks are predominantly mafic rocks. That's shown in this geologic map here in green is all the mafic rocks. There are some TTGs which are shown in brown, and some chemical sediments which are shown in yellow. In the data that Rick actually showed in his talk was from an extinct isotope system. There's an isotope of samarium-146 that has a half-life about 103 million years. And so it went extinct before 4 billion years ago. And so the accrual of this 142 neodymium isotope only has meaning up until about 4 billion years ago. But chemical signals where there are excesses or deficits of 142 neodymium relative to the modern terrestrial composition gives us an indication that the mantle had to melt before 4 billion years ago in order to have that signature. In this diagram here, I'm showing this 142 neodymium isotope composition on the y-axis against the 147 samarium isotope composition, which I'm using as a proxy for 146 samarium here, because 146 samarium has gone extinct. And what you can see for these rocks, what Jonathan O'Neill and colleagues have found is that these ones here, which have the filled in diamond symbols, are relatively mafic rocks from this unit that are not zircon bearing, so we can't date them directly. But luckily, lines in this diagram have age significance. And so this line here that's fit through these in the modern Earth has a slope corresponding to an age of about 4.3 billion years old. And so what this has been interpreted to indicate is that these rocks are 4.3 billion years in age. Like everything with the Jack Hill zircons, though, of course, this is something that has been debated too. But regardless, the preservation of these 142 neodymium isotope signatures that are different from the modern Earth do indicate that these rocks formed at the expense of a Hadean aged reservoir. Rick also showed this plot in his talk last week. And what it's showing is the 142 neodymium isotope composition over time from the formation of the Earth to the present, and looking at it in a variety of terrains compared to the modern mantle. And so the modern mantle is this band in gray here. And one thing that's important about this is not only can you date rocks directly, as we were trying to do here in the superior craton at the Nuvvuagittuq supracrustal belt on the last slide, but you can also use it for rocks that post-date the termination or the extinction of 146 samarium at 4 billion. You can look at subsequent rocks and look at these signatures in them as a way of getting a sense about the survivability of these Hadean reservoirs. And so ultimately we're getting information about continent survivability at that time. So the preservation of these 142 systematic, or these compositions and rocks from Isua here indicate that they formed at the expense of a reservoir that had been fractionated in the Hadean. And so that's really important for thinking about survivability of Hadean aged crust. And to come back to that a little bit and make sure that that gets reinforced and then carry on to talking about some crustal growth models as well, I wanted to highlight why these radioactive isotope systems are so powerful. And essentially what happens is when Earth's mantle melts, the radioactive parent element and the stable daughter isotope element are fractionated from one another because they're geochemically different. And so the way that I want to illustrate this for you is showing this diagram here. We're looking at the concentration of a given element normalized to the bulk Earth. And then the elements on the y-axis or x-axis here are going from incompatible, so ones that go into melt preferentially, to relatively compatible ones which stay behind in the mantle preferentially. So if I had a starting composition of a primitive mantle, if you follow my cursor here, it would be a line that would be a flat line about here at 1. And then if I were to melt that, I leave behind a residue. I don't totally melt the mantle, I partially melt it. The residue that I leave behind would be this depleted mantle line here. And so this is the elemental composition of that reservoir. The melt that I extracted, that partial melt, would be the continental crust or would be a mid-ocean ridge basalt, depending on what tectonic environment I was in. So as you can see the continental crust here, it's extremely enriched in some of these elements compared to the depleted residue that's left behind. So for the samarium neodymium isotope system, where there's a radioactive isotope of samarium that decays to a daughter product of neodymium, you can imagine that if I have this hypothetical flat line of a primitive mantle here, the relative amount of samarium neodymium is set on this diagram. But the depleted residuum that I leave behind has a different samarium to neodymium ratio, as does the continental crust. And so it's actually this differential partitioning behavior, or these differences now in the samarium and neodymium that are imparted, that we can capitalize on to start evaluating when mantle melting happened and the extent of mantle melting that happened. In this plot, or in this slide, what I want to talk about is the isotopic evolution of Earth's depleted mantle. So on the left-hand side here, I'm showing for the non-extinct isotope of samarium that decays to neodymium, it has a half-life many times the age of the Earth in this plot. We can track the evolution of Earth's depleted mantle with time. So what we do is we take the most juvenile rocks we can possibly find, which today are mid-ocean ridge basalts, so they're up here. And if we track back in time and attempt to do this for the different rocks that we have, we can track what the neodymium isotope composition was and what that's telling us about this differential partitioning of samarium versus neodymium. So the oldest rocks we have are about 4 billion years old, and their neodymium isotope compositions are higher than the bulk Earth. The bulk Earth in this diagram, by definition, is set to 0. So this is tracking this depleted mantle reservoir over time. Below this plot, I'm showing a plot of the hafnium isotope evolution of the Earth over time. And the one thing I just need to tell you about this is shown in this plot on the right, which is that hafnium and neodymium co-vary in the modern Earth. So if we go measure them in the modern Earth, they behave relatively similarly. And that's because if I come back here, and if we look at the radioactive parent of lutetium that decays to the daughter product of hafnium, these relative slopes here for the depleted mantle reservoir and the continental crust reservoir are similar to how they would behave for samarium and neodymium. So if I come back here and look at this covariation, I would expect that when neodymium is positive, I would expect hafnium to be positive. And that makes sense in the modern Earth. We see that with mid-ocean ridge basalts. They're both positive for these two different parameters. When we go back to 4 billion years ago, that's not what we see. We see negative isotope compositions for hafnium in these oldest rocks and positive isotope compositions for neodymium in these oldest rocks. And so this is a bit of a quandary. It does come down potentially to where neodymium and hafnium are sitting in these rocks and what the stability of the phases that they are in and their susceptibility to metamorphic alteration. But another thing that's important about this is that these records are actually used to make inferences about the establishment of crustal reservoirs on the Earth and the crustal volume through time. And so we need to kind of reevaluate these records sometimes because some of them feed in this data and we haven't totally resolved what the neodymium isotope compositions in the earliest Earth truly mean. So this recent model here by Juan Rosas and Jun Cornaga feeds in data from the plot that I just showed you on the last slide. It's just the time axis has been oriented the other way here. So here at the early Earth, we have these really positive neodymium isotope compositions up through mid-ocean ridge basalts today. And then this plot here is showing the data that Rick Carlson also showed in his talk for the extinct 146, 142 neodymium isotope system. So this data has actually been fed into a model for self-consistency with the evolution of Earth's depleted mantle over time, and they've produced a crustal growth model trying to infer how much continental crust there was at a given time in Earth history. And that's shown with this blue line here, and it basically calls for a very rapid establishment of a continental crust reservoir approximately the size of the modern crust in the Hadean, and then some sort of maintenance of that reservoir through production and recycling and destruction over time. But this isn't the only crustal growth model that exists. There's actually a whole spaghetti plot here of them. And so this plot is showing from the formation of Earth to the present on the x-axis, the fraction of continental crust relative to today. So a value of 1 is where we are today. And so all of them converge on this point here. You can see that there's major disagreement about how the volume of crust has accrued over time. And as I said, it's a spaghetti plot. It's like if you took a handful of spaghetti and just threw it at the wall. The red and orange and yellow models that are kind of warmer colored here are conceptually ones that call for early establishment of a large continental crust reservoir. Here's the Rosas and Cornaga one we were just looking at, and then some sort of maintenance of that volume over time. These colder color ones are more protracted, advocates of protracted crustal growth, where the continental crust reservoir grows incrementally over time. As June Cornaga has recently pointed out, though, you can classify all of these models in different ways, and so they don't really belong on the same plot together. So the ones on this plot belong together, and they're ones that he refers to as crust-based growth models. And these models basically aim to estimate the present day distribution of crust that we see. And so it's a lot more difficult with the kinds of data sets that feed into this to account for crust that may have existed, but with its record was destroyed, and we no longer have record of it at our surface. So ultimately, these end up serving as a lower bound on net crustal growth. And to give you a sense for that, this purple line here by Goodwin is documenting actually the surface age distribution of crust on Earth today. The other end member are mantle-based models of net crustal growth. And so this basically estimates the history of net crustal growth by evaluating the depletion of Earth's mantle over time. And so here's that Rosas and Cornaga model we were just looking at for neodymium isotopes, because they were using the neodymium isotope record that tracks crustal compositions as a way of indicating how the depleted mantle has changed over time. Ultimately, these models are more favorable according to Cornaga, and I think I can best exemplify this in this diagram here, where if we classify net crustal growth models as ones like this red line here, then you have to think about the recycling and also the reworking of crust over time. So recycling is going to be destruction and removal of crust, and then reworking is going to be taking crust and reusing it. And the difference between mantle-based models of net crustal growth and crustal-based models that we were looking at 2 slides ago is actually this parameter of crustal recycling. And if you look at the crustal-based models and you remove all the crust that has been reworked, you can actually get back to the surface age distribution. So I think this new classification scheme is going to be a really important part of our discussions moving forward on evaluating all of these relative crustal growth models. I want to come back to something else I mentioned too, which is that it's really difficult to evaluate this when the record of the rocks themselves has been destroyed. And so if you've produced crust and destroyed it, and we no longer have it at our surface, how can we possibly account for it? One creative approach to this that was put forward by Steve Parman several years ago is basically an idea of punctuated tectonic evolution. And in order to understand the graph at the right, I just kind of want to give you a sense of what he did. So globally, but here's an example from North and Central America. He looked at sediment in 500 million year age bins. So here's sediment from 4 billion to 3.5 billion. We scoot up here from 1 billion to 500 million years ago. For each of these packages of sediment, he looked at the detrital zircon uranium lead age distribution, so just the age of crust that was weathered into these sediments. And you can see that for the oldest rocks, it's not very complicated. The black line is actually showing you that age distribution from 4 to 3.5 billion, and lo and behold, that's the age of the zircons that are in that sediment. But as we march forward in time, you can see that it becomes a much more complicated story. So for these rocks here that are 1 billion to 500 million years old, you can see that the age distribution incorporates much older crust into it. So with this level of accounting, what Steve was able to do is build up this schematic model that I'm showing here on the right. So on the x-axis, we're looking at age going back in time from today back into the Hadean here. And on the y-axis, we're looking at the total volume of continental crust through time. And so this is his proposed crustal growth model that is a schematic model here. And feeding into that are these different periods. So this period here, almost to the end of the Archean, is a period where the destruction of crust outweighs the production of it. So even though you might have a relatively high production rate over this period of time, the destruction rate outweighs that. And so you actually don't have a lot of crust preserved from this time period. And then for the end of the Archean and for most of the Proterozoic, it seems that production could have outweighed destruction. And then on modern Earth, we actually know that production and destruction are about equal because we can go to subduction zones and account for how much material is being produced there and destroyed there and start kind of doing that mass balance. Another question that we can ask is, how has the composition of the continental crust changed over time? This is a really nice statistical sampling study done by Brendan Keller and Blair Shaney, where they looked at over 70,000 different samples from the igneous rock record on the continents. And they did this both for mafic rocks and felsic rocks. The plots that I'm going to show you here are just focused on mafic rocks because it's a lot of data to look at. And what they essentially did was they looked at a variety of geochemical parameters. So here's an example here for rocks that are 40 to 50% by weight of silica, so relatively mafic rocks. They looked at them over time, and they looked at a variety of major element and trace element parameters. So here's the potassium oxide concentration. And then what they did is they did a weighted bootstrap Monte Carlo resampling of this. And so that's what this is showing here in this diagram is a sample of that. And everything gets smeared out because there's quite a bit of age uncertainty with a lot of these units that have been measured. And ultimately in that resampling, they generated a trend over time. And so this is the ultimate thing that you'll be seeing these plots on the right. What they see here are a variety of trends from 4 billion years ago to today. And as you can imagine, we have more rocks concerning this today, so it's much more precise today than earlier in Earth history. But essentially, what they see are some really large shifts in major element parameters such as magnesium and trace element parameters such as nickel. And essentially, these are consistent with mantle cooling over time. And you see that compatible and incompatible elements in basalts are gradually decreasing over time, or they're documenting a decreasing melt fraction over time, pardon me. And that's actually shown here in this last plot here, with apparent melt percent plotted versus time, with higher melting percents in the Archean and relatively low melting percents in the modern. And so what ultimately this is showing is a change in crustal composition over time, and that there are some pretty large scale changes potentially recorded in the igneous record. On top of that, there are a variety of other studies that have looked at trace element compositions to evaluate similar trends in sediments over time. So I'm going to go through a couple of these very quickly in the interest of time. This is some work done by Marion Garçon in the Barberton Greenstone Belt, which is located in southern Africa in the Kapval Craton. And in this greenstone belt, there are a variety of sediments. And she looked at all these different types of sediments and characterized their samarium neodymium isotope compositions. And she was able to correlate that directly with their silica content. And so she was able to say they actually have a lower silica content on average than the present day upper continental crust. And so this is suggesting ultimately that there was more mafic crust exposed in the Barberton greenstone belt relative to felsic continental crust than we see exposed today. Similarly, Ming Tong et al. Have done this by looking at trace element ratios in shales and diamictites over time. And so this is showing nickel versus cobalt over time from the mid-Archean through the present. And essentially what they're doing is they're using these trace elements as a proxy for magnesium oxide because magnesium is soluble. And so they're trying to evaluate how mafic rocks were over time, but using trace elements that are less easily disrupted by weathering. So if we zoom in on this transitional point that they see here from really high values kind of coming down to lower values, this is what that looks like. And when they do this, they can make inferences about the magnesium oxide concentration over this interval. So ultimately that's what's shown in this plot down here on the left in blue, is that the magnesium weight percent in the upper continental crust started higher in the Archean and it was decreasing over time through this interval that I was just highlighting. And they can do some calculations and kind of make some inferences based on that and thinking about magnesium mass conservation ultimately. And they've inferred that there's been a significant change in the amount of mafic rocks exposed in the early Archean versus the late Archean. And so that's shown here with more basalt and komatiite relative to granite exposed in the early Archean and then less komatiite and basalt exposed in the late Archean relative to granite. This is actually in conflict with a lot of work that's been done recently. And the question has been reposed in some of these more recent studies, which is not are the relative proportions of mafic to felsic crust changing over time, but instead, is it just the mafic and felsic crust changing it's themselves, like their actual composition? And that's more consistent with that Keller study that I was showing you a few slides ago. So this proxy here that I'm showing in the left-hand plot is the titanium isotope composition of rocks. And it's based on the observation that in igneous rocks, this ratio correlates with silica concentration. And so that's shown here. What's great about this is that felsic rocks have high values of titanium isotope compositions and mafic rocks have a value of 0. And so in this plot over here, that's actually showing that with these green and red bars respectively. When these authors went and measured this in a bunch of fine-grained marine sediments over time, this is ultimately what they saw. What they saw essentially was that there was no large change in the titanium isotope composition of these sediments through time, indicating that the relative proportions of mafic rock or felsic rocks and mafic rocks over time had not substantially changed. And so their conclusion is that the proportions of mafic to felsic crust aren't changing, but really it's the mafic and felsic crust themselves that are changing. This is further corroborated by a very recent study that was looking at the trace element compositions in these same kind of marine rocks over time and evaluating how they fluctuated over time. And they worked out that, yes, the mafic and felsic crust themselves were changing compositionally in terms of their trace element compositions, but that ultimately didn't mean that there was a significant change in time of the relative amounts to felsic to mafic crust. And so here you can see the proportion of felsic to mafic crust does change over time compared to the present, but it's not as substantial as some of these earlier arguments may have been making. Another major chemical change that has been measured over time in rocks has been the oxygen isotope composition of zircons, which is something we talked about earlier in the context of the Jack Hill zircons. So this diagram here is looking at the oxygen isotope composition over time. Here's the Hadean Jack Hill zircons here, and you can see that some of them have values higher than the mantle zircon value, which is this yellow bar here. Another thing that you'll notice in this diagram is in the Archean, the maximum values of zircon compositions are about +7 per mil for oxygen isotope compositions, but it broadens significantly after about 2.5 billion years ago, or the GOE, the Great Oxygenation Event, or the Archean Proterozoic boundary. And so one thing that this might be indicating is that higher degrees of subducted sediment are being incorporated from this time forward, or some other sort of process related to low temperature alteration of rocks at Earth's surface. And basically this ties it back to process. Plate tectonics is the easiest way to subduct crust. And so one more thing to talk about before I close my talk up is, what do we actually know about when plate tectonics start on Earth? The answer is that there's a lot of disagreement about this. This diagram here is showing the different ages at which plate tectonics initiation has been proposed on Earth. And you can see they range from about 4.2 billion years ago based off of the inclusion assemblages in the Jack Hill zircons being granitic in nature, all the way up to almost the end of the Neoproterozoic here. And all of these depend on different arguments and also different characterizations of what plate tectonics actually is. And to help clarify that a little bit, I want to come back to why isotope tracers, like I mentioned earlier in this talk, are maybe our best bet for deciphering tectonic environment. One of the more diagnostic features that we would actually use are rocks that are produced in subduction zones. So they're direct evidence of subduction in plate tectonics themselves, such as blue schists. Unfortunately, the record of blue schist doesn't go very far back in time, and so it's difficult for us to evaluate if that's a primary record or if blue schists have been preferentially destroyed over time, or they aren't readily preserved in older rocks for some reason. So the things that are easier to focus on are things like isotopic recycling, which we can actually use back through the entire rock record. And so that this actually goes back to the earliest rocks here, and you can extend it back further, I think, into the Hadean to look at Jack Hill zircons as well. And I'm not going to get into the nitty gritty here as much in this diagram, but what I just wanted to show you here is that there's actually a complex set of interpretations about what kinds of tectonic settings there could be for the oldest crust. And it can involve impact reworking of superficial magmas. It can involve delamination and removal of material from the crust because it's relatively dense, and so kind of flow of crust. It can involve stacking of mafic rocks and then remelting of mafic rocks at depth when there's a sufficient amount of material built up and thickened in a plateau. And so this comes back to some of the tectonic environments we already talked about, like this one here proposed for the Jack Hill zircons. There's a non-plate tectonic model for basically forming these zircons and getting water to sufficient depth to generate granitoid magmas. There are other models that are non-plate tectonic too, like this catalytic delamination model proposed by Jean Bédard. And in this case, what happens is a mantle plume comes in and melts and generates magmas. And then crustal density differences and the residual mafic material differences dripping back down can actually spur more magmas coming in. And you kind of get this catalytic cycle coming in and flowing crustal structures. And then finally, we can also talk about plate tectonic type. Plate tectonics operating in maybe mobile lid type scenarios in the early Earth. And so I'm giving one last example, coming back to isotopes as I always do, looking at half-new isotopes in zircons as a way of tracking a change in magmas on the early Earth. So I'm showing a plot here on the left-hand side of the half-new isotope composition. Remember again that the bulk Earth falls along this line of 0 here, of rocks over time in the slave craton. So the Acasta Gneiss complex, and then also more broadly the slave craton around it. What this record is showing is that the oldest rocks that are up to 4.02 billion years old here have negative isotope compositions consistent with even older material in their generation, which is really beautiful. We're looking at some of the oldest rocks we have, and we have evidence for even older rocks in their formation. And then reworking of that material over time. And actually, if you follow my cursor here, the slope is showing the reworking of that material, and then it suddenly stops, right? There's no more data underneath my cursor over here. Instead, what happens is relatively juvenile materials input in this area at this time. So everything kind of comes back up to more positive values, and then those get reworked over time. So there's attenuation of the reworking of this oldest Hadean reservoir. Another thing we see is input of juvenile magmas here. And then these magmas here are actually documenting positive compositions, which is indicating the mantle is at least somewhat depleted in this area by about this point in time. And this is missing an age axis here. I apologize for that. This is 4 billion years here, and this is 3.6 billion years here. And then this would be 3.2 right here. On the right-hand side, I'm showing some diagrams that are outlining what the possible plate tectonic scenarios could be to generate this isotope record that we're seeing here, in tandem with a variety of geochemical parameters, such as trace and major element compositions that we have for these rocks over time. For example, understanding when their lanthanum and terbium ratio changes and when you actually have to go to deeper generation depths for the formation of the magmas. So this top panel here is showing a tectonic environment 4 billion years ago, so forming these oldest rocks here, actually these first two magmatic generations. And what we have envisioned is that there is a Hadean protocrust sitting at Earth's surface at that point in time, and so that would encompass this part of this diagram where we actually don't have data, so over here in this part of this diagram. And then that Hadean protocrust basically there's heat pipe volcanism that impinges on the Hadean protocrust, forms a bunch of volcanoes, and starts building up the crust here. And as it over-thickens, you get a thickening pile here, you can start to remelt and generate magmas. And so that's shown in pink here. And the pink compositions are corresponding to these first two magmatic generations in the slave craton, showing remelting of that Hadean protocrust. Then, 3.6 billion years ago, we come down to this panel here. And we see inception of mobile tectonics at this point in time. And this is largely based on trace element evidence for a shift of melting depth in combination with these hafnium isotope signatures. And so if we think about a piece of juvenile oceanic crust that's just formed, it's got something maybe close to the mantle composition or primitive mantle composition at this time. And if you were to subduct it and remelt it, you'd be mixing this composition with all of these older compositions here from remelting of Hadean materials. And so that's what this orange value or this orange region is trying to show in this plot, demonstrating that this shift back up to more primitive or juvenile compositions here could indicate inception of mobile tectonics at this time. It's actually something that we see in a variety of cratons, so not just in the slave craton, but you can see that this is mirrored very nicely in the Wyoming province. You can see it somewhat in the Jack Hill zircons over time, and the Singboom craton, among others. And so this shift to a relatively juvenile source is shown in all these purple lines at different points of time in these cratons, and might indicate that this is tracking mobile tectonics in a variety of places globally within about a 200 million year window. So in conclusion, there are a lot of questions and not a lot of firm answers. So the first thing that we talked about was, when did subduction begin and when did plate tectonics start? Oh, that's the most recent thing that we've discussed. And basically there's a paucity of record of rocks in the Hadean and the early Archean, and the extreme degrees of metamorphism that some of these rocks have experienced, or the multiple stages of metamorphism, and also the potential for alteration, makes it really difficult to evaluate. As I mentioned before too, there's different criteria for evaluating the start of plate tectonics, and the definitions of what plate tectonics constitutes themselves, as Brad Foley will get into, have varied over time. And one thing we can say, if we look back at that timeline we're looking at for all the different propositions for when plate tectonics initiated, most people agree, most researchers agree that by about 3 billion years ago, we may have seen plate tectonics. Has the volume of continental crust changed over time? This is a really difficult one too, as we saw that there was that spaghetti plot with a variety of models, but the most recent work is arguing that some of these models don't really belong in that plot on the same basis. And so it's possible that the rapid accrual of a crust in the Hadean was likely on this basis, but that needs to be further discussed as well. And then ultimately, has the composition of crust changed over time? And what does this tell us about what rocks were exposed at the surface and available to be weathered as the basis for nutrients available for life? And some people argue that the proportions of mafic to felsic crust have changed over time, but more recent papers have started constraining that it's actually the mafic and felsic crust themselves that have been changing. And it seems like that's where the strongest evidence lies for now. Thank you for listening, and I'm looking forward to discussing this with you on Friday.